machine learning. I lead a group called the AI User Experience Team inside of Google Research. One of the things that means is that I will not be talking to you about the Google Assistant or how to integrate it into any of your IoT devices. I'm sure a lot of you know or have made trade-offs around that well before I came up. Instead, what I want to talk to you about are the things that we discuss in the hallways of Google Research as we're thinking about how to apply machine learning to future technologies. Now, I know that this audience is really diverse in terms of skill sets. We have people here who are engineers. For some of you, this might be going a little slow, but other parts will hopefully go faster. We have people here who are product folks, CEOs, accountants, salespeople, and I'm told UX people as well. So, let's see how well we can get you into the water cooler at Google Research, given that variety. So, machine learning is a subset of artificial intelligence work, and it's used for all kinds of things. This is one of my favorite examples. It's from something called Project Magenta, which is a project we have inside of Google that uses machine learning to autocomplete music. So if you're working as a composer, you can say, hey, I'd like to have this kind of break in the middle of my song, and the system will try to figure out what an appropriate piece of composed music would be for you. We also use machine learning in all kinds of things. In Google image search, for example, we use machine learning to understand what the entity of a cat is, so that when you do a search for cat, we can pull that up. So it's used in all kinds of places. Google Translate is another example. We use machine learning to brute force understand the meaning between the corpora of multiple languages and provide you with a translation. So that's sort of what the ML stuff is about. We'll go into a lot more detail about how machine learning works. But I wanted to preview the three things we'll be talking about. Number one, the future of machine learning and computer science as I see it. Bear in mind that I am a user experience person with a psychology background. That'll come up. Number two, what bags of potato chips might have to do with that future. And number three, how product learning can catch up to the learning rate of our machines. Okay, so let's start with the future of machine learning, which is right here. Now, every time I look at this picture, it raises all kinds of new questions for me. But we'll come back to this one. First, let me tell you about me, because along the way, I'll tell you about some products that will fit into the rest of the story. So I, like I said, am a human factors psychologist, a cognitive psychologist, so the kind with the lab coat, not the kind with the sofa. And I started out working at Boeing on the development of automated cockpit systems. This is some of the things I studied. I went to Google, worked in the advertising group, and then was brought in to work on the self-driving car systems. Now that's a spin-out company called Waymo. I also worked at a place called X, which was an incubator for all kinds of ideas, including smart contact lenses. And we asked a lot of questions about what the future of miniature computing would look like. Then I went back to Google to join Google Research. We worked on a lot of other interesting applications. This is one called AIY, which is a way for us to take some advanced machine learning technology and make it available and sort of democratized. And you could actually pick up these kits at Target. I think they might still be for sale. I'll tell you more about that later. My team also worked on something called Google Clips, which is a small standalone camera that has no viewfinder. And the idea here is that we would use artificial intelligence to automatically take photos that the user might want. And that allowed us to do all kinds of things. It allowed us to experiment with the concept of bringing computers into what is basically a creative task, right? Like, people pride themselves in photography. My wife is a photographer. And here the question is, how much can a computer provide a delightful experience? It also allowed us to work on things like privacy. This system was developed with on-device machine learning, so all of the photos that it would take would actually be saved on the device. All of the inferences would happen on the device, and then the device would actually ask its owner whether it wanted to save those photos. The human wanted to save those photos. So it was referred to as an oddball piece of technology, which is basically like my CV obituary will hopefully have that in it. And then we went on to put that same technology into other places. So we looked at the things that worked, we looked at the things that didn't. We first developed something called Photo Booth, which is available live on any Pixel 3 device, if you have one of those. It's in the camera. It's sort of in the happy experiment section. And Photo Booth, the way it works is it actually just, you turn on that mode, and when it thinks it's found a photo that it likes, it takes the photo for you. So imagine you're in a group selfie situation, and there's always that, like, you're taking like 1,000 pictures so that you can try to catch everyone when they're not blinking and smiling. So Photo Booth does that automatically. And then we extended that into what's called Pixel Top Shot, which is a similar idea. We take a burst of photos when you ask for it, and then the computer system will actually determine what the most likely really great photos are within that burst. So if you ever had the experience of taking a photo of something that was maybe in action, like somebody playing a sport, and then you realize that you just missed the photo, Top Shot allows you to go back in time and pull that photo. So let's go back to this photo, which I think is a really interesting one. So the guy in the left is John Watson. He was the founder of the Behaviorist School of Psychology. And what he's doing, aside from it being really weird to grab a baby by a pencil that the baby's gripping onto and having a nurse, desperately trying to make sure that baby doesn't fall, is he's trying to understand what learning looks like for humans. He's trying to understand what are the things that people came into this world with, in this case, grip strength, and how early does that develop. So I mentioned that because he's very famous for starting the Behaviorist School. The Behaviorist School was a reaction to a previous school of psychology called introspectionism. And in introspectionism, you ask people. So you say, hey, did you see that thing? And people say, yeah, I saw it, or no, I didn't. And what we were discovering in the course of psychology was that people were wrong a lot. People would say that they had reasons for making decisions, and it turns out they didn't. So what Watson did is he said, let's just ignore what people think about their own minds. Let's just sort of put that aside, and let's pretend that all human thinking happens inside of a black box, or like a fleshy box. And all of that thinking is made up of data input that goes into the black box and a behavior that comes out the other end. That's not unlike the way a lot of our machine learning models work today. So a computer receives a lot of information, goes through a statistical process not unlike the one happening inside the brain, and then comes up with a prediction and a course of action. He was also famous for pushing a process of experimentalism. So in the past, when people might come up with other ways of reasoning, what Watson and the behaviorists said was that it's really about doing controlled experiments. Step one in a controlled experiment, you observe, you come up with a question. Then you hypothesize, you take a stand. So you say, I think that this thing happened because of that. You put your bias out into the world, and then the next thing you do is you create an intervention, some way of testing whether that bias, that hypothesis you had, is true or not true. Then you learn from it. So you put it into the world, you see what happens, you observe, you take measurements, and then you go back to the beginning and you say, based on what I observed, what's really happening? And then in the end, hopefully you are really happy your theory winds up being true or true enough, and then you go forward. And that process of experimentalism is also what we do when we're doing product design, and it's also how artificially intelligent systems work today. So let's go back to Pixel Top Shot. I mentioned it briefly. I gave you guys a sense that this was a really cool product, and it really is. We have some really cool stuff coming up in the next version too. But this is what I said. I said, it's an AI camera that takes great photos. And the question that should come to mind for everybody is, what does that mean? Like, what's a great photo? Who says that it's a great photo, right? How is the photo taken? Who's in a great photo? Are we all in a great photo? Is it a photo of me? And what are they doing that makes that photo great? The next question you should all be asking is, do people want this kind of photo? When we created the Clips camera, it was partly a test to see if in the real world we could create value by putting this camera out there and allowing, in that case, it was targeted toward parents who want to capture moments of their children growing up. And then the next question is, do we have the technology that can actually deliver on all those things? So let's go back to our black box. The way the Clips camera worked and the way Top Shot works and the way a lot of these AI systems work is that you first create a training data set. So you take a set of photos and you say, these are all really good photos. We're going to allow the black box system to figure out what a good photo is. And then you also add expertise. So in our case, we had professional people curating and rating photos, both the ones that we fed into the black box, and then we also had them on the other end looking at the photos that came out of the black box. Like, was the Clips camera able to take photos that professional photographers thought were worth saving? And that's really the process that we have to go through when we deal with artificially intelligent systems. Like, what are the feedback mechanisms that we're building in? What are the values that we have as a company or as a developer? So, which use cases are we willing to allow? Which ones are we going to proactively stop? And then as it's performing, is the model working the way we intended it to? And does that match with what the customers actually want? So, Pixel Top Shot, easy thing to say. Years of development to figure out how to get through that loop and to continue collecting data and then to figure out what the next version of this thing might be. Okay, so first thing, future of machine learning and computer science is a return to the same experimentalism that we had 100 years ago, because that's one of the best ways that we have to interrogate what's happening inside of these systems, and it also provides us a framework that we can use when developing intelligent devices. Okay, so let's talk about potato chips. First, I want to make sure that everybody is on the same page when we talk about machine learning and one other tricky concept. So I have a little video here for us to watch.
Let's play a game. Close your eyes and picture a shoe. Okay, did anyone picture this? This? How about this? We may not even know why, but each of us is biased toward one shoe over the others. Now imagine that you're trying to teach a computer to recognize a shoe. You may end up exposing it to your own bias. That's how bias happens in machine learning. But first, what is machine learning? Well, it's used in a lot of technology we use today. Machine learning helps us get from place to place, gives us suggestions, translates stuff, even understands what you say to it. How does it work? With traditional programming, people hand code the solution to a problem, step by step. With machine learning, computers learn the solution by finding patterns in data. So it's easy to think there's no human bias in that. But just because something is based on data doesn't automatically make it neutral. Even with good intentions, it's impossible to separate ourselves from our own human biases. So our human biases become part of the technology we create in many different ways. There's interaction bias, like this recent game, where people were asked to draw shoes for the computer. Most people drew ones like this. So as more people interacted with the game, the computer didn't even recognize these. Latent bias. For example, if you were training a computer on what a physicist looks like, and you're using pictures of past physicists, your algorithm will end up with a latent bias, skewing towards men. And selection bias. Say you're training a model to recognize faces. Whether you grab images from the internet or your own photo library, are you making sure to select photos that represent everyone? Since some of our most advanced products use machine learning, we've been working to prevent that technology from perpetuating negative human bias. From tackling offensive or clearly misleading information from appearing at the top of your search results page, to adding a feedback tool on the search bar so people can flag hateful or inappropriate autocomplete suggestions. It's a complex issue and there's no magic bullet, but it starts with all of us being aware of it so we can all be part of the conversation. Because technology should work for everyone.
Our team did such a great job putting that story together that when I want to talk about it, I almost never try to just do the voiceover. I think that video is a lot better. It's very short. If you look me up on Twitter, you can also find that video and then just share it to other people. So let's talk about the implications from that video. There's two important ones. The first one is that artificial intelligence is about learning in order to predict and to take an action. And number two is that it learns precisely what we teach it. So we're the ones who get to decide what these systems are like, who they react to, who they benefit, and who they don't. And it's really tempting for a lot of people working on the development of devices to just say, like, let's leave the ML to the ML experts. But it's not about the ML experts. The ML expertise is about the statistical models and how well they perform. But the real question for us is, what kind of product do we want to make? You know, who are we choosing to include and who are we choosing to not include? Here's an example. Suppose you were creating some kind of Internet of Things camera, maybe designed to work in a garage opener. Depending on where you do the training, your garage opener may work or it may not work, right? So if you're looking at Swedish cars, you will have a detector that's biased toward certain types of cars, certain brands, and you may miss cars or motorcycles or three-wheel devices that might be used in other parts of the world. And this is something that that fit between the thing that you started with and the market that you're trying to get to is what we in psychology call generalizability. Generalizability is a poorly understood topic, I think, generally in the world, and also an area of very active research inside of machine learning. So it's something that we talk about a lot when we're developing these models. We're also getting to the point where these models are available for reuse. So, there are vendors out there. I've spoken to people who use vendors to buy a classification model or a face recognition model. And in many of those cases, you don't really know what the training set was that's underlying those weights. So a very active topic of research right now is what's the kind of nutritional label that can tell you where data were collected and what the developers of that think it'll generalize to. For many people in this room, I would advise that if you're working with vendors, ask them. Ask them where were the data collected, what's the underlying data set that produced this before going ahead and integrating that. Okay, so like a bag of potato chips, which has an ingredient label in the back, machine learning development has an obligation to understand what the ingredients were that made up the product that we're in. Now let's talk about the rate of machine learning, how quickly these products are going, and more things that we can do to catch up. There's also a few resources that I'll point you to in case you want to follow up on this afterwards. So this is the Google Edge TPU chip. It's an accelerator for machine learning calculations. That is a US penny. So these things are getting incredibly, incredibly small. And their ability to do inference on a device is becoming incredibly interesting to people who are doing this kind of development for lots of reasons. One is the things that used to be done inside of a supercomputer sitting in the cloud can now be done locally on something that fits on a penny. Many implications to that. One of them is privacy. So if you have a device that you don't want communicating with the cloud, like our Clips camera, you have the ability now to use technologies that allow the data to remain on the device and under the control of the user. That's a question that often comes up around artificial intelligence. Another one is field deployment. So if you're Lufthansa, for example, and you're concerned about all of these devices having to go talk to the cloud and then make the round trip back, you are now able, and I don't know if Lufthansa has any interest in any of our chips, by the way, but you have the ability to deploy these things in a field. So you can literally put it into a farm field. You could put it on a far out remote place or a place with limited connectivity and still be able to take advantage of this. Now, a lot of companies are making this. I think all of the big tech companies have invested in their own chipsets. One thing that we've been talking about a lot in Google Research is how we can take this technology and make it more and more democratized so that more and more people can experiment with it and more industries can adopt ML technologies. I mentioned this earlier. This is the AIY kit. The first versions of it were targeted more at makers and consumers. We made it possible for you to make your own Clips-like cardboard camera. We made it possible for you to make your own Google Assistant cardboard device. And what we've learned from that, as part of that product learning we talked about earlier, is that there's an appetite for this kind of prototyping tool that uses the latest chipsets in industry generally. So I think in a month, we're putting out a new set of edge TPU reference boards of various form factors and shapes so that other people can use the same technology in a professional context all the way up to manufacturing. This is one of the things that happened with that first generation, part of our learning process and our feedback mechanism. We partnered with a group called KidMob and with our friends at Autodesk, and we did a design sprint with children who have unusual limbs and allowed them to create their own machine learning enhanced devices to give themselves superpowers. It was a really amazing story. I think it was picked up by a couple of news outlets, and there's videos out there that you can see. Our own Kristen Olsen on my team worked on that. She's up in the corner. And so, when we're working on all of these things, the main thing we're thinking about is what's our feedback mechanism? What's the mechanism by which the system is going to learn, and what's the mechanism by which we're going to learn about the system? And those two things have to happen in tandem. Because not only are we thinking about that loop, but we're also thinking about what's the logical progression of this technology, and what's the logical progression that we agree with for the technology to have. Now, I mentioned I was going to share some resources. We have a group called PAIR, People in AI Research, that my team supports. They do meetups around the world, cross industry, and we bring in lots of academics, and they've produced a lot of content. Some of that content is available on design.google. That's actually a website, and you can go and take a look at articles like 6 AI terms that UX people should know. So if you want to go back and share some of the things that you've learned here, or some of the thinking that you have around AI, feel free to go there and pass that along. Okay, so let's go back to the third thing. If the first two things are true, then the third thing is that our devices can learn. So how are we learning with them? And a lot of that has to do with educating the design teams and moving from a mindset of we're making hardware and we make the hardware and it goes out into the world, to one in which every level of the hardware is actually a prototype for what's coming in the future. And those are mind shifts that we have to make both with our design teams, so we have to train them up, with our product teams, who have to be thinking longer term than they were able to before, and with our hardware and software engineering teams, who also need to be able to see through what the next generation might look like.